at continue to look at the colligative properties, but in this one we're going to look at osmosis. Now, osmosis is the movement of a solvent through a semi-permeable membrane from a region of lower solute concentration, higher solvent concentration, to the region of higher solute concentration, lower solvent concentration. Wow, that was a mouthful. So basically what we're trying to do is move the solvent through a semi-permeable membrane, which is a way of saying that you're going to move it through a membrane that only allows the solvent particles to come through. This is like using, a doggy door. Most people can't fit through a doggy door, especially if it's for little dogs. So that would be your semi-permeable membrane would be the doggy door, and the solvent would be your little dog, because you're a bigger particle, you're not going through. Now, biology does this as well, but biology looks at it from the solute particle viewpoint, which kind of drives me insane, because they're looking from the lower solute concentration to the higher solute concentration. And that doesn't make any sense, because we're looking at the solvent moving around. So I'll show you an example of this, and it'll make more sense as we look at it. But just remember that if you look at what is actually moving, it's easier to keep with it. And the other thing that you need to remember is this is a colligative property, so watch your numbers, because things that involve salts will have different osmotic pressures or properties than will molecular. So if we look at this is a solution where we have moving it through a semi-permeable membrane, and it's always going to move from high to low. So if you look at this side, it has a lot more solvent particles. And because it has a lot more, it's going to move to the side from more to less. Okay, so what happens is this will continue to move, and when it moves down, it's going to move down here and rise over here. And if you look at the difference in the height column right here, this is the osmotic pressure. This is the pressure it would take to stop osmosis. Once it moves to the level where basically the solvent particles are uniform on both sides, then it stops moving, it's level. Now, if you apply a pressure and you force them to go from a region of low to high, then this is called reverse osmosis. And we'll look at this again. Osmosis. We'll look at this a little bit later in a slide, because this is how some places like the desert countries, California does this on Catalina Island, they use a reverse osmosis to produce potable water. Okay, so the trick is that if you look at this from a solvent viewpoint, then this would be the pure and this would be the solution. So the solution is automatically going to have less solvent particles in it because it has more solute particles. Okay, so if you play a mental game where like you only have 100 particles total, if you have 60 that are that's way too high. If you have 30 that are solute, then that means you have 70 that are solvent. If you have 40 that are solute, that means you only have 60 that are solvent. So you're going to move from the 70 solvent to the 60 solvent, because there's always going to flow from high to low. Again, more about this as we go. But before we get to looking at the actual particles, we need to be able to define osmotic pressure. Now, we did gas laws back in 1211, so you don't have to go back and review them. You just need to follow along. You should remember P equals nRT. If I rearrange to solve for P, then I end up with N over V, which is your molarity. See, this is molarity. Okay. And we also have to take into account the particles because this is a colligative property. So if we substitute this in for that, we're going to end up with this equation here. Now, this is the giant pi. This stands for osmotic pressure. So if you'll notice, osmotic pressure deals with molarity, not molality. Kf and Kb deal with molality. If you'll look at the units of your constant, you're fine. Now, the temperature here must be in Kelvin. Remember the gas laws. And your gas constant here is 0.0826 liter atmospheres per mole K. Do not use the one that we used in the, we will use it later in the kinetics labs where it has energy. We're going to use the R factor that involves the gases. So, if we use this, the osmotic pressure of a solution of 5 grams of horse hemoglobin, so I'm going to call this HH. So horse hemoglobin, we have 5.0 grams. And our solvent is going to be water. And we have 1 liter of it. We're told that our osmotic pressure is 1.8 times 10 to the minus 3 atmospheres. Okay, and this is at 25 degrees C, which remember that's 298.15 K, because remember K is equal to 273.15 plus degrees C. Okay, and we want the molar mass. So we want the molar mass or the molecular weight, so that's grams per mole. Which means that we know we have given our grams. So let's look at it. Pi is equal to IMRT. This is a molecular compound. I is equal to 1 because it's molecular. And if you don't know that protein is a molecule, it's a molecule. Okay? So we're told that we have 1.8 times 10 to the minus 3 atmospheres. And I is 1. So we're looking for our molarity, 0.08206 liter atmospheres per mole K. And our pressure has to be atmospheres if we're using that 298.15 K. And we know that because our units need to cancel. So our molarity is going to be equal to 1.8 times 10 to the minus 3 atmospheres divided by 0.08206 liter atmospheres per mole K. And our K is 298.15. So again, our K's cancel, our atmospheres cancel, and we've got 1 over liters per mole, so that means it's going to flip over. So we end up with a molarity of 7.357. Let me erase that so you can read it. So my molarity is equal to 7.357 times 10 to the minus 5th. That's how many moles per 1 liter. And we're told that the volume of solution is 1 liter, so that leaves us with 7.357 times 10 to the minus 5th moles. Molecular weight is equal to grams per mole. So if we look up here, we've got 5.00 grams per 7.357 times 10 to the minus 5th moles. So we end up with 67961,636 grams per mole. Wow, that's large. So that's 68,000 grams per mole. Now, because we said this was horse hemoglobin, which is a huge protein, we are perfectly okay. So if you get a really, really large number, that doesn't mean that you did the math a lot wrong. If you get a small number, that doesn't necessarily mean you did the math wrong either. It's just a function of what the compound is you're looking for. If you get a negative value, that's an issue. Go back and check your math. Okay, so that brings us to diffusion. Osmosis is the movement of the solvent. Diffusion is the movement of a solute through a semipermeable membrane from a region of higher solute concentration to a region of lower solute concentration. And so the solvent concentration is not involved in diffusion. Osmosis is only the solvent, but you have to take into account the solute concentrations in order to figure out how much of solvent you have. In the case of diffusion, you're only looking at the particles in there, and the flow is always high to low. Now, diffusion is really how when they do dialysis on kidney patients, that's really what you're doing is you're using diffusion. Okay, so let's work a problem. Now, here's an osmosis problem. There's one, you're probably going to have one like this on the exam where you're going to be asked which direction the flow is. And what you're going to need to do is take into account what you have and what's going on. So what you want to do is always look at the center and see what we're looking at. So this one is sodium only. So if we look at it, this has 3 sodium particles per compound, so we're going to multiply this by 3. 3 times 4 is 2, carry the 1, so it's 4.2 molar. That's in sodium only. This one only has 1, so we're going to multiply by 1. So we're looking at 2.8 molar on the right-hand side and 4.2 on the left-hand side. And again, I like to screw up left and right, so I like drawing arrows, but we'll look at left and right here. So if we're looking at solvent only, we're going to flow high to low. So that means we're going to flow this way. Okay, that one's really straightforward. Now on this one, we're going to flow solvent only. So in this particular cases, we need the number of particles total. So over here, we actually have 4 particles, 3 sodiums and 1 phosphate. So we'd multiply this by 4, so that's 16, carry the 1. That's 56, 5.6 molar. Over here, we would end up with 2 particles. So we multiply by 2, so we get 5.6 molar. So wait a minute. We have the exact same concentration on both sides of solute, which means we have the exact same concentration of solvent. Therefore, in here, because they're the same, then there will be no net flow. All right, well, that doesn't help you out in terms of other problems, so let's look at a second example here. We're going to keep the 5.6 molar over on this side, but let's say that this one is 6.2 molar instead. So what direction is the flow going to be? Well, it's going to flow high to low, so obviously it's going to flow towards the 6.2. And this is where some of you are like, wait, no, that's this bigger number. It's the bigger number of solute particles, which means you have less solvent. So remember back to if you have 100 particles and you have 20 on this side and 20 particles over here and 30 particles over here. If you have 30 particles, that means you have 70 particles of solvent. 20 particles is 80 particles of solvent, and solvent is high to low, so 80 flows to 70. Now, of course, you don't have 100 particles. However, you've got to figure out a way to make this work for you. In biology, they teach you it's going to flow from the lower solute concentration to the higher solute concentration, which for those of us that think if you put something on top of a hill, it's going to roll down the hill, everything flows downhill. This doesn't work well for me. So if that works well for you, you keep it. But if you're on the chemistry side, we don't care about the solute other than how many we have. We're looking at the solvent. So that's what happens on that one. So back to our diffusion. And remember, this is diffusion. This is osmosis. And this is diffusion again. Now, the osmosis problems, I know that there are a couple other ones posted. There's at least one video, and I'm pretty sure there's another problem that's just a problem with the key posted. So you may want to look at that. This one is looking at bromide only. We have 0 molar on the sodium phosphate because there's no bromide. We have 2.8 molar on the sodium bromide because we've got it there. So again, it's going to flow high to low. And as I said, you'll have a problem similar to this on the exam where you're asked which direction it's going to flow. Now, this brings us to blood cells in different solutions. And oh, somehow I skipped a slide. And I'm like, wait, that was the cool slide. So before we get to the cool slide, which is critical for IVs and stuff, let's talk about what we're going with. We're going to use two solutions, A and B. Isotonic solutions mean that solution A has the same concentration as solution B. In the case of osmotic pressures, they're equal. So if it has the same isotonic, means that you have the exact same concentration. Now, hypotonic and hypertonic are relative to which one you're dealing with. So if it's hypertonic, you're going to say that solution A is less concentrated. This is hypo, like hypoactive, is less concentrated than solution B. So what that means is the osmotic pressure of A is less than B. And in that case, we say that A is hypotonic with respect to B. Hypertonic means that solution A is more concentrated than solution B. So we say that A has a greater osmotic pressure than does B. Now, you need to make sure you understand which one you're talking about, because if you have solution A and it has an osmotic pressure equal to 0.85 atmospheres, and solution B has an osmotic pressure of 0.95 atmospheres, then we would say that B is hypertonic with respect to A, or we could say A is hypotonic with respect to B. So what's the right answer? Tomato, tomato. It depends upon which one you're starting with and looking at. So be very aware that whichever solution they're asking you to start with, you want to compare that to the second solution. Okay? So why do we care? Well, these are the good slides. So this shows you why this is critical. And this is critical because if you're ever in the hospital, you're going to need, and you may need an IV, you want an IV that is isotonic. Because if you put an isotonic solution in your bloodstream, your red blood cells don't shrink and they don't get any larger. They just stay happy as a clam. But if you put them in a solution that is hypertonic with respect to the red blood cells, then what ends up happening is all the liquid comes out of the red blood cells, and you get something called crenation, where they form this icky thing like this, which is bad because then they're still not carrying oxygen where you really want to breathe. So, and the other case is if you put them in a solution that is hypotonic with respect to the red blood cells, what goes on is that you end up with hemolysis. So the red blood cell is hypotonic with respect to it's got a higher concentration, so all the solvent wants to go in, and it's like a balloon. You keep adding more air and it's going to bust. So this is why it's critical that you get IVs and fluids, etc., that are isotonic with whatever you need. Now, this is a text from the previous Pearson edition, and I like this one because you can actually get a better picture of the blood cells, what they actually look like. This is crenation, and this is hemolysis, where they're swelling and they're going to blow up. Okay, now this was a figure that I got from a Brooks Cole text ages ago, and this is my practical application. This is how pickles are made. If you take a cucumber, yeah, they're kind of crunchy, but they're not anything like a pickle. And what you do is you take the pickle and you put it in a solution that's high salt vinegar, so that's a weak electrolyte. So you got lots and lots of particles in there. So all these particles make the solution hypertonic with respect to the cucumber. And so all of the water comes out of the cucumber into the brine solution. And that's why that's why they're crunchy. The other thing is this is critical for keeping food from spoiling. Now, we have refrigerators and freezers and vacuum sealers and all these good stuff. But back years ago, and in some places where it's hard to come by different items, they used to pack things in salt, smoke them, and packing them in salt is the equivalent of basically sucking the water out of everything. So when you suck the water out of like, let's say, a ham or a fish, then the bacteria cannot survive. So therefore they cannot spoil the food. The same thing with adding sugar, lots of it, to fruit juice. It's called jelly. And it's a way to preserve the fruits, meats, etc., if you don't have access to a refrigerator or a freezer. Okay? And this is a closer look at the Van Hoff factor. We went through it as ion pairing, but in this closer look, they go through the same thing we pretty much did. So if you didn't quite catch it all, you can find the Van Hoff factor in this section right here.